Hello everyone, welcome to the video on line of best fit. So last video we talked about residuals, which we're going to use that concept to talk about line of best fit. So we talked the last time about how some residuals are positive, negative, and if you add them together, they actually cancel each other out to add up to the sum of will be 0. So it doesn't do us any good to do that. So kind of like with standard deviations, where the same thing happens, is we're going to square the residuals and then add the squares. And then as it says here, the smaller the sum, the better the fit. So the smaller the residuals are as a total, the better that line fits, the closer that line comes to all the points. And we want the one with the smallest residual sum, and that is it's called the least squares line, the line of best fit. We looked at this last time. Y equals mx plus b is how you write the equation of a line. In statistics, we use y hat equals a plus bx. Y hat meaning the predicted y value from that line of best fit. We use b for the slope instead of m. We use a for the y-intercept instead of b. All right, so here's a formula for calculating the slope. R times standard deviation of y divided by standard deviation of x. That's going to give us our slope. And then call from this, we have y hat equals a plus bx. Y hat equals a plus bx. So if we're going to write the equation of our line of best fit, we need two things. We need to know the slope, which is the formula that we just looked at a moment ago, and we need to calculate a. So what they've done to get this formula is they subtracted bx from both sides. And get y hat minus bx equals a. Or a equals y hat minus bx. So assuming that we've already calculated b using the formula on the previous slides, we now need something to put in place of y and x to solve for a, the slope. Well, it turns out that every single line of best fit, all the line of best fits you've ever calculated, drawn, and it was never pointed out to you before, every single one of those lines contains the point x bar, y bar, which is mean of the x's, mean of the y's. That ordered pair is on every line of best fit. So what we're going to do is we're going to place x with x bar and y with y bar, because that point will be on our line of best fit. So we're going to practice doing this over here. So here I've got a set of data. This is games played by a football quarterback and the number of completions total. So 23 games played, 510 completed passes. I've got the sum of the x's. Here I have the sum of the y's, standard deviation of the x's, standard deviation of the y's. So first thing we have to do is we have to calculate the slope of our line. B equals r times standard deviation of y divided standard deviation of x's. So slope is r 0.9524, 24 times standard deviation of y divided by standard deviation of x. All right, and that equals roughly 25.61. Now remember, that was the change in y, standard deviation of y, over standard deviation of x. Now remember, our y variable was completions, so this numerator is completions, and our denominator x, that was games played. So this would be 25.61 completions per game. So that's the interpret the slope part. What does that number actually mean? We got to think of it in terms of in context, in terms of y over x. So it's completions per game, 25.61 completions per game. So we've got B, and in our model, we still need A. So we're going to go back to here. And remember, it's A equals y hat minus bx. A equals y hat minus bx. And we're going to replace y and x with x bar, y bar. So we're going to have A equals, for y hat, we're going to put y bar, the mean of the y's. B, our slope, times, that was the mean of the y's. We're going to place x with the mean of the x's, and that's going to be 37. Right, so that equals A equals negative 132.07. And we want the y-intercept in context. Now, got to be careful sometimes. We keep saying that none of these line of best fits are perfect. They're just models, because what this now means is, because that's the y-intercept, and the y-intercept x is 0. We're now saying if you play 0 games, you would complete negative 132.07 passes. Of course, we know that if you played 0 games, you would complete 0 passes. So in this sense, it doesn't make sense in context. We would want more data. We might actually want to put the 0.00 in here to help create a better model. But anyways, in context, that's how you read that. So now our final model is y hat equals negative 132.07 plus 25.61. Oh, I left out the x. Okay. And so now if we wanted to estimate how many completions a quarterback would have after a certain number of games, we would plug that number in. Now, one thing you have to be careful of, and this you'll see this later in the slides, is something called extrapolation. Is this data was built from a low of 23 games played up to a high of 49 games played. So when you start estimating outside of the range of data that you use to create it, you're say we're playing with fire there, you're in dangerous territory. That's not very good. Just like using the 0, this would now tell us that 0 games played, you complete negative 132 passes. Well, that turns out to be poor because we're outside of our range of values that we used to create it. Right, let's try another one. Okay, so I had to make some corrections here as I went through this a second time, as you can see. All right, so we've got our data here. This is car rentals, and this is in miles that you have driven it for one day, and this is your cost for the day. Turns out we've got our mean for the x's, mean for the y's, and standard deviations for x and y's and r. So we want to run through the same thing. So see if you can stay one step ahead of me and solve for B. All right, so here we go. B equals R times standard deviation of x, standard deviation of y. It's always change in y over change in x, just like slope. So the y variable over the x variable, 63.31. Right, so this gives me roughly 0.33. And again, in context, what does the slope tell me? Remember, it's the y variable over the x variable. The y variable was the cost in dollars, and then the x variable was miles driven. So dollars over miles driven. So we're talking about, this would represent 33 cents per mile. So that's our cost, 33 cents per mile. Now we want to find the y-intercept. Now if I look at this graph, my y-intercept looks like it's pretty close to 20. I don't think we could see it on the previous one, but here I can get a pretty good estimate because I can visually see it. So I'm expecting something around 20, but let's go ahead and calculate it. So you guys take a moment and calculate it. All right, so we're going to go back. We're going to use a equals y hat minus bx. And again, we know somewhere on this line is the point 173, 76.83. So 173 is about right here. So this point right here is roughly 173, 76.83. Right? On every line of best fit, you will find X bar, Y bar. So Y bar is going to be 76.83 minus B, which was about 33 cents. Remember, we're doing some rounding here. And as you work with rounded numbers, the next step will be off just a little bit. And then times X, which is 173. Okay, so I did my calculation for A, and I get A equals, and I have 19.74. So again, y-intercept in context. So remember this point here, because it's on the y-axis, that's when x is 0. So we're saying if you have driven 0 miles, your cost is $19.74. So that's probably like the daily rental fee, right? So on average, it costs you $19.74 per day, and you have to pay for the mileage. So that's why your formula, your prediction model is going to be y hat equals, you're going to start at $19.74. Remember, the y is the cost. So we're creating a model for the cost, plus 33 cents for every mile.